Hi everyone. So now we're going to talk about velocity versus time graphs. So in addition to graphing position versus time, we can also graph an object's velocity as a function of time. So for example here, we have an object on the left, this motion diagram. We've got equidistant displacement values here, but we can graph its velocity as a function of time. So we can just do a quick analysis. We know velocity is displacement over time, so we can see that their velocity is going to be 10 meters per second. So, and it's going to be a constant 10 meters per second. So here we can graph on the graph below that at each second we know its velocity is 10 meters per second. Here also on the right we have a situation where the object's accelerating, but we can also graph its velocity versus time. So if we say perhaps had an apparatus or the car was looking at its speedometer and saw what its instantaneous velocity was at each of these times, we can actually tell from this graph what the instantaneous velocity was at each of these points. So at time equals 1 second, we see that its velocity is going to be 4 meters per second. At 2 seconds, it was 8 meters per second, and so on. And here we have a best fit line connecting all our data values. So let's think. What is the meaning of the slope behind a velocity versus time graph? So here we have velocity on the y-axis and time on the x-axis. So what does the slope tell us? So use the process that we looked at from the position versus time graph and what the value of its slope meant, and determine what the slope of a velocity versus time graph says. So slope is rise over run. Our rise here, our y-axis, is velocity. Our time is going to be our run. So our x-axis is time. So a slope is a change in those values. It's going to be a change in velocity over change in time, and that's acceleration. So the slope of velocity versus time graph tells us the object's acceleration, and that's pretty cool. So we can analyze these graphs qualitatively, right? So qualitative means without numbers. So here on my y-axis for the velocity, I just have from going from slow to fast, right? And that's even also in the negative direction, basically going from slow speed to fast speed. So in this object here, or for this object, we have the situation where we have our velocity versus time graph having a positive constant slope. So as you see from a velocity, going from a slow velocity to a faster and faster velocity. So we're speeding up, and since the slope is constant and it's a positive value, it means we have a constant positive acceleration. Here for this this object, we have the situation where we're going from slow to fast. So again, we're speeding up, but we're speeding up in the negative direction. And we can also see that its slope is a constant negative value, so we're going to have a constant negative acceleration. Here on the right, just the two other situations we can have here is we go from a faster speed to a slower speed. So in this case, we have a positive velocity because we're in the positive region of our graph. So our velocity is positive, but we're slowing down, so that means our acceleration is negative, and we can see that from our line getting having a negative slope. Conversely, we have here an object that's going from a faster speed to a slower speed. Velocity is negative here because we're dealing with the negative part of our graph. So velocity is negative, right? It doesn't become positive until possibly it crosses over to our positive region of the graph here. It doesn't show that happening. We have a negative velocity, but because the slope is positive, it means our acceleration is positive, and that's why we're going from a more negative value for velocity to a less and less negative value, smaller, going from faster to slower. So pause and think. So my first question for you is, what is the acceleration of object 1? Object 1 is this graph up here. What is the acceleration? So we see here our acceleration is going to be 0. The reason for that is the acceleration is going to be the slope of this line. This line has no slope, it's a flat line. The slope is 0, so our acceleration is 0. Does this make sense? It should. As we see here, this is basically saying that our velocity has a constant value, whatever that value is. Since it's staying the same, we're not accelerating. So it makes sense that our acceleration is 0. My second question for you is this velocity of the object 1 positive or negative? Well, the velocity is positive, and the reason for that is our line is in the positive region of our graph. 3 asks, what is the acceleration of object 2? Object 2 being this object here. The acceleration again is 0 because this line has no slope. It's staying at a constant velocity, so its acceleration is 0. Part 4 asks, is this velocity of object 2 positive or negative? Hopefully you answered negative, and the reason for that is that this line is in the negative region of our graph. Now, in addition to the slope, for a velocity versus time graph, we can actually analyze the area under the line and what that means. So let's say we had this situation here where we have a constant velocity of 5 meters per second. And we're analyzing, let's analyze it for the first 3 seconds. So if we're traveling 5 meters per second constantly, after 1 second, we're going to travel 5 meters. And then if we go on for another second, we're going to be at 10 meters. And then after 3 seconds, that's going to be 15 meters. Now, one thing to notice, our area, so I symbolized area with a capital A here, so careful, don't confuse that with acceleration. Acceleration is always going to be a lowercase a. Our area is going to be length times width, or base times height, or however you're going to define area for this graph. So our length here is 5 meters per second. Our width is going to be 3 seconds. So we find the area, so that's going to be this region here. It's going to be 5 meters per second multiplied by 3 seconds, and that gives us a value of 15 meters. So that was pretty cool. So the area under our velocity versus time graph tells us the object's displacement. Right, so we can calculate displacement by calculating the area of this graph. Now, why do I put under in quotation marks? The reason for that, so here what I mean by under is going to be the region between the line and our x-axis. So in this case, our time axis. That's going to be the area under the curve. I say curve, it can be a line or a curve. The reason why that term under is kind of confusing is because we can actually have a negative value, as we'll see on the next slide. Our velocity can be negative, right? We can have a negative velocity, why not? When we're dealing with the area under the curve, then it's going to be the region from above that curve, actually. The area between that line and our time axis. And we'll see that in just a moment. So, another pause and think type problem. The first question here asks, what is the object's displacement after 5 seconds? So 5 seconds in this case would be from this point on the graph, our 0 seconds, up to this point here, and that being 5 seconds. We want to see what the object's displacement is. So we're going to do that by adding up the areas. So here is actually the same situation we had on the previous slide. The area under this curve is going to be 5 meters per second multiplied by 3 seconds gives us a value of 15 meters. But then we also have to worry about this area here. And because this is below our axes in the negative region, we're actually going to consider this a negative area. And we have a triangle here, so we can very easily do 1/2 base times height. So we can consider this here. We have a height of -5 meters per second. We multiply that by our length. Our length here is 2 seconds. So we have to multiply that by 1/2 because we have a triangle. So it's going to be 1/2 multiplied by -5 meters per second multiplied by 2 seconds. That gives us a value of -5 meters. So then if we add up our total area, we have a value of 15 meters here in this region, plus our negative 5 meters here. So that means our displacement after 5 seconds is going to be 10 meters, a positive 10 meters value. Question 2 asks what is the object's displacement after 7 seconds? This here isn't too difficult just because we have here, we already know this is going to be 15 meters displacement from time 0. We have here negative 5 meters. We can use symmetry to solve the rest of the problem because all we need is the area of this region here. Well, we see that these areas are actually the same value, just one's going to be negative, one's going to be positive. So they're actually going to cancel out. So in a sense, if we had this problem without even doing part 1, we could have just solved for this and realize that these would cancel and not even have to number crunch those areas. So our answer is going to be 15 meters. Because we have our 15 meters from this region here. We add our negative 5 meters here plus 5 meters here, gives us a value of 15 meters. So our displacement from time 0 to 7 seconds is going to be 15 meters. All right, and then finally, if our object started at a position of 5 meters, what is its position after 7 seconds? Well, since we know our displacement is 15 meters, and if we started at 5 meters, then after 7 seconds, we're going to be at a position of 20 meters. And finally, I'm just going to tag this onto this video here. We have acceleration versus time plots. So here we can literally read off this graph and see that we have our object's accelerating. At time equals 0, we have an acceleration of 1 meters per second. And after 1 second, we're accelerating at 2 meters per second, and so on. So we can literally read off the acceleration as a function of time. We could also plot this value as well. So let's see what the slope means. So slope is going to be rise over run. In this case, we have acceleration versus time, so it's acceleration divided by time. This is our change in acceleration over time. This is a value called jerk. In a sense, it's the rate of change of acceleration. So how fast our acceleration changes, which is, as you can imagine, if you were in a car that had some sort of jerk value, you'd get jerked around. So we're not worrying about jerk in this class. So in a sense, the slope of an acceleration versus time graph is not going to be useful to us. The next thing we can analyze is area. So we do the area under our curve or line or whatever it is. It's going to be length times width in a sense. Just doing some unit analysis. Our length, our rise of acceleration, that's meters per second squared, multiplied by our times being seconds. We see that gives us units of meters per second. That's units for velocity. So the area under our acceleration versus time graph is going to tell us velocity, and that's going to be helpful to us. So in summary, dealing with all our position, velocity, acceleration graphs, we can, here's a little table with what values help us determine what in what situations. I do not recommend memorizing this table. I think it's kind of pointless. Well, the table itself is not pointless, but memorizing is pointless is what I meant to say. So basically, my helpful hint here is if you can't remember what the slope tells you or what the area tells you in a certain situation, just do some unit analysis. What I did back here on this previous slide here, dealing with units on the graph, that tells us what our answer is.